Research by Researching Democracy. I tell you what, John, let's just give everybody 1 minute to take a breath, and we'll try to start right at 10:30.
Sounds
good. My estimation for what 1 minute would look like was overestimated. 5 seconds for a breath. I hope everybody breathed in that short moment. John, if you want to go ahead and take it away.
All right, thank you. And thanks for having me here. And I'm really happy to be a part of this group and to be here talking with all of you today about these important topics. So the title of my talk is Democratizing Research by Researching Democracy. And what I'm really going to do is give an overview of some of the projects that I have worked on with students over the past 15 years or so, and 15, 20 years, I guess. And then I'll introduce you to some of those students. And then towards the end, I'll reflect a little bit on why I think that voting theory is such a great avenue for introducing students to research, and some of the suggestions and things that I've perhaps learned over the years from my experience in doing this kind of research with students. So I'd like to start by looking at an example of the problem that first got me interested in voting theory research when I was an undergraduate. So for this example, I want you to assume that we have a geographic region where there's two central cities here. So think Minneapolis, St. Paul, Dallas, Fort Worth, something of that sort. And assume for the purposes of this example that these cities have pretty good transportation infrastructure between them. So whether that's bus systems or subway or whatever it is, there's good public transportation between these two cities. But what's lacking is transportation from the suburbs, noted here with A and D, into the central cities. So the Department of Public Works for this county is proposing to build a light rail system. They want to levy taxes to do so. And they're going to allow the voters to make a decision on whether we should go forward with this project. But we're going to do it by putting 3 different proposals on the ballot. First one is, should we build the light rail connection between A and B? Second one is, should we build the light rail connection between B and C? And the third is, should we build the light rail connection between C and D? Okay, so you may have seen elections like this in your own states or communities. There's certain locales that are very well known for having these types of referenda with multiple questions on the ballot. For instance, California often has, I remember one election with 27 different statewide proposals on the ballot. So the way that voting works in an election like this, it typically is that we vote on each proposal separately. So voters would go to the ballot box and they would register a yes or no on proposal 1, a yes or no on proposal 2, and a yes or no on proposal 3. So here's an example of how voters could vote. 26% voting no on all 3 proposals, 24% voting yes on all 3 proposals, and then various combinations in between there. Now, if you add up the votes here, the way we add up votes in an election like this is, again, by proposal. So if you look at the first proposal, there are, let's see, 26% plus 10% plus 15%. There are 49% that vote yes, 51% that vote no. So the first proposal fails. If we look at the second proposal, so looking at just the middle column here, proposal 2 passes. 54% of the voters voted yes, 46% voted no. And proposal 3 fails. 49% yes, 51% no. So what happens here is that we end up only building the BC connector, which was the least needed option. B and C are already pretty well connected. And also, nobody voted for that. Not a single person voted no, yes, no. Nobody really wanted this. It's a pointless and redundant course of action. And conceivably, this is not only not the first choice of any voters, but it could conceivably be the last choice of many, if not all of the voters. And it's not too hard to construct examples like this where you do have an outcome that is the last choice of every single voter in the election. So what's going on here is something called the separability problem. voters' preferences on certain proposals depend on the outcomes of other proposals. So let's take a look. The voters who voted yes, yes, no. These are voters who wanted the AB connector and the BC connector. Maybe these are voters who commute from the suburbs out at A into either B or C. They probably only want the BC connector if the AB connector is also built. The BC connector is of no use to them if they can't get from A to B. These voters might say, well, if I'm going to be able to get from A to B on light rail, it might be more convenient for me to just continue on to C on light rail as well, not have to transfer to a bus or whatnot. But these voters would most likely not want just the BC connector. So the problem is that these voters are voting on all three proposals at the same time. They don't know if proposal 1 is going to pass when they vote on proposal 2. And when we aggregate the votes separately, we end up with these problems where essentially the interdependencies get ignored. Voters can't express those interdependencies and the voting system can't take them into account either. So preferences that don't have these kinds of interdependencies, where a voter's preferences on one proposal might depend on the outcome of others, are said to be separable. We've seen an example here of where non-separable preferences can lead to election outcomes that are at best unsatisfactory, sometimes even paradoxical. And I point back to the example of a winning outcome that is the last choice of every single voter. Now, separability is not unique, and the separability problem is not unique to voting theory, to referendum elections. It actually was studied first in economics and has important applications, modern applications in operations research and computer science. But it was first observed in referendum elections in the late 1990s, which happened to be when I was an undergraduate at Calvin College and I needed a senior thesis project to work on. And so this is where I was introduced to the problem and where I started exploring it. So some of the mathematics, just to introduce some definitions, we can formalize this idea. This is sort of a semi-formal way of defining what separability is. We could say if we have a referendum on a set of questions, a subset of that set of questions is separable with respect to a given voter if the voter's preferences for the outcomes on the questions in that set don't depend on the outcome of the election for questions outside of the set. So for example, if we say that the singleton just containing the first question is separable, what that means is that the voter can specify their preferences on that first question, either yes is better than no or no is better than yes, without having any information on the outcome of the remaining questions. If we say that a set of questions, for example, the set containing questions 1 and 2 is non-separable, what this means is that the voter could not specify a complete ranking of the 4 possible outcomes on these questions, so yes, 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 no, no, yes, or no, no, without having at least some information on the outcome of other questions in the election. So this leads to some interesting and natural mathematical questions about separability. Since we can talk about what it means for sets of questions to be separable, we might ask some set theoretic questions about that context. So if 2 sets of questions are separable, is their union separable? Is their intersection separable? Of course, we could talk about symmetric differences and things of that sort. And in other words, if we look at the structure of the set of separable, the collection of separable sets for a given voter, what can we say about that collection set theoretically? And this is actually, this is a question that was studied in economics back in the 1950s, and it led to a very famous theorem called Gorman's theorem that said that in the context of economics, when we're looking at commodity bundles, pretty much separability is preserved by just about every set operation you could think of: unions, intersections, symmetric differences, things of that sort. The way that we conceptualized this question for the context of referendum elections was to define a notion called the character of a voter, which is just the collection of all sets that are separable. And then the question becomes, what is the structure of the character? If the character of a voter contains all of the possible subsets of the question set, then we say that the voter's preferences are completely separable. This means that every set, the preferences on each set can be expressed independently of knowledge of the outcomes on other sets. And if the character doesn't contain any non-trivial subsets of the question set, that means the preferences are as non-separable as they could be. By non-trivial subsets, I mean subsets other than the entire question set and the empty set. Then we'd say that the voter's preferences are completely non-separable. So completely separable preferences are the nice ones. That's what we're looking for. These are ones where voters have no problem expressing their views on all of the different questions simultaneously. Completely separable or completely non-separable preferences are the bad ones. Those are the ones where the voter can't tell you their preferences on any subset of questions without having some information on the remaining questions. So characters give us a way to talk about how separable a voter's preferences are. You can imagine in between completely separable and completely non-separable, there's a whole bunch of structures, a whole bunch of collections of sets, which leads to an interesting inverse problem, which is if we have an arbitrary collection of subsets of the question set, can we find preferences that are separable on exactly those sets? Can we reverse engineer preferences? Now at this point, we've stepped away from the practical application of the separability problem in referendum elections and just let our mathematical curiosity kind of run wild. But there are applications here, and one of the applications is simulation of referendum elections. If we want to simulate and test the effect of separability on the outcomes of referendum elections, we need to be able to represent the different types of interdependent structures that can arise in voter preferences. So that's one of the applications. This question becomes a mathematical curiosity, and it turns out it's one that has a lot of interesting mathematics involved in it. So we ask, if we're given a character, can we find a preference order that has that character? If such an order can be found, we call the character admissible. And it turns out that characterizing admissible characters is a really hard problem. Finding the characters that are admissible is not trivial at all. It turns out that every character must be closed under intersections. That is the one part of Gorman's theorem from economics that carries over to the discrete context of referendum elections. But closure under intersections is not sufficient. For example, here is an example of a character for a 4-question election that is not admissible. What is more interesting is that this is the only character up to isomorphism in the n=4 case that is not admissible. It's the only one out of 165, which is puzzling. And we still don't know why. We still don't know. We can construct a proof that says this character is not admissible. We can explicitly find preference orders for all of the other 164 characters. We're just not quite sure how this generalizes. And we really know nothing about the structure in general for elections with more than 4 questions. So this was an observation first made by my student Micah Terhar in 2003. This picture is interesting because where Micah is the Rayburn House office building at a poster session intended to showcase undergraduate research for members of Congress. It's called Posters on the Hill, and I believe it's still running. So he was able to present his work at this session, and I had a number of students extend this work from that point forward. So here are a couple of my REU students, Jenny Dubas and Mark Krinis. Mark went on to get a PhD in computational mathematics and social science from University of Iowa. And he actually studied social choice theory for his PhD. They wrote his dissertation in that area. But they proved this result that the really bad preferences are actually the most prevalent ones. And so that was sort of an interesting but disheartening structural result. My students Beth and Sean from the 2013 REU I don't know how they'd feel about me using this particular picture of them, but it's one that I like. They looked at using graph theory to study this character admissibility problem. And the idea was that if we construct certain types of graphs and label the vertices with the outcomes of an election. So in this case, this graph has one vertex for each outcome in a 3-question election, where 1 represents a yes and 0 represents a no. Then we could look at Hamiltonian paths in these graphs, and maybe those Hamiltonian paths and the characters that they generated would have something to do with the structure of the underlying graph. And they in fact proved that this was the case, and were able to demonstrate that you could construct certain characters by looking at these hypercube graphs. So it extended, it's not a complete answer to the character admissibility problem, but it gave us another class of characters that could be constructed explicitly. The next couple of years, I had 2 other groups that continued this work, looking at different types of graphs and how the characters that resulted from those graphs could be predicted from the structure of the graphs. And then I also had, throughout this time, another thread of research that was much more practical. So I've talked about some very theoretical mathematical questions that involved mainly, proof-based work for students that had that more theoretical background. But I also had a thread going for students who were more interested in simulation and some of the more practical questions. Pete Schwalier, who's now a high school teacher and tennis coach, he ran simulations to study the actual effect of separability on the outcomes of referendum elections. In other words, if we just simulate a bunch of elections and vary the degree of separability within the electorate, can we say anything about how that impacts the kind of outcomes that are selected? And the short answer to this is that separability significantly increases the chances of electing the best outcomes and decreases the chances of electing the worst outcomes. In other words, if we can force preferences to be separable, we will get rid of some of these paradoxical outcomes. And the extent to which we get rid of the bad outcomes is proportional to the percent of the electorate that has separable preferences. My next 2 students on this thread looked at how we could use an alternative voting system to yield better outcomes in referendum elections. Clark has now finished his PhD in applied mathematics from Brown, and Ada is a pediatrician finishing her residency now. And I mention that just because the students that I'm showing you, many of them have gone on to graduate school, many of them have taken jobs in industry, many of them have gone on to non-mathematical careers. And I believe that these sorts of research opportunities have been beneficial for all of those groups. So Clark and Ada had the idea of a system that contrasted from the way that we typically vote on referendum elections, which is we all come in on a given day, we cast our ballots, and the outcome is announced after all the votes have been cast. What if we use that as a starting point and allowed voters to recast their votes over an extended period of time with the results of the election based on the votes that have been cast so far announced in real time. So people start to vote, we see how the votes seeming to shake out, and that gives us some information on what direction different proposals might be trending. And maybe as a voter, if I see that, I want to change my vote to take into account some of the non-separability in my preferences. So we ran extensive simulations and found that this iterative method was at least as good as simultaneous voting in almost 97% of our trials. Iterative voting was better than simultaneous voting in close to half of all of the trials, and significantly better when it was better. And iterative voting was only worse in 3.2% of the trials And when it was worse, it was only worse by a little bit. So we concluded that this would be an interesting and novel, though perhaps hard to sell method for resolving the outcomes of referendum elections with non-separable preferences. I want to just mention a couple other projects before I wrap up here. In addition to the work on the separability problem, which kind of got me started in this area, I had a couple of students in 2008 define a convexity-based measure of gerrymandering and calculate this convexity-based measure for all 435 congressional districts, and also prove some interesting theoretical results about that. Emily and Jeff both went on to get PhDs in mathematics. And one of the things that made this project so exciting to be, first of all, we published in the College Math Journal, which was really exciting, and we made the cover of it. But also, Emily, when she finished her PhD and became a faculty member, she came back to Grand Valley and was a mentor for the 2018 REU. So 10 years after she was my student, she mentored 2 students of her own in the same program. And that was just really exciting. And I love to see when my students go on and continue work in this area. She actually became a graph theorist. So her project that she mentored was in graph theory, not related to what we did, but it was just exciting to see her continuing to mentor students in research projects. And then I'll mention the last 2 students here I'll show, Rachel Roca and Caitlin Patel. Rachel's here at the conference today, and we'll be talking about random sample voting later on. That was my most recent project, and they were part of the 2019 REU, which is the last project that I did. So I'll let Rachel tell you more about random sample voting later this afternoon. So just a few thoughts here to wrap up. I would say voting theory is a really nice area to introduce students to research in mathematics. And I think that's true for a number of reasons. One is there's lots of relevant and applicable topics that lend themselves to students with lots of different interests and backgrounds. So if students have more of a proof-based background, there are theoretical questions to answer. If students are more interested in applied and computational mathematics, there's all sorts of simulation-based projects that can lead to really interesting results. Part of that is that the prerequisites, the entry point for these projects tends to be minimal. Some of that is the newness of the field and the relative recency with which voting theory has been studied from a mathematical perspective. But some of it is also just, I think, the nature of the field lends itself to creative thinking that doesn't require 3 or 4 years of reading to get to the main point. And I think that that's really a nice feature of the field for undergraduates who are interested in doing research in this area. So some of the advice I would give if anyone is contemplating starting a research program with students in this area is just to start small. You don't have to start with an externally funded program. You can start with an independent study project. It doesn't have to be something that's necessarily going to lead to publishable results. Pick an interesting question and explore it. If it's new to you and it's new to the student, it's a valuable experience. I think that one caution I would give is to be careful to pitch your work in an audience appropriate way. This is an area where when you're talking to political scientists, the work can be too mathematical. When you're talking to mathematicians, the work can be not mathematical enough. I'll say this in terms of how you communicate results, but also how you communicate with your colleagues, especially if you're a faculty member who is untenured. You have to speak the right language and convince people of the value of what you're doing, especially if it is not using. Well, I will say that I have been criticized. I was criticized during personnel reviews for not doing graduate level mathematics in my own research, which it was an intentional choice on my part, but, and I happen to be in a department that that was an outlier in terms of the criticism. Most of my department was very supportive of this. But you do have to communicate your work in a way that others can understand it and sell the value of it. I'd say be flexible with their topics and what your definition of success is. It looks different for different students. And one of the things that has been most beneficial in my work with students is just letting the students own the project and letting them go in directions that you would not necessarily anticipate. Some of the best results have come from ideas that I never would have thought of. We work with these brilliant students. We need to let them be brilliant and not try to be too narrow and micromanage projects. If you're getting used to this area, you can browse the archive. The Game Theory and Computer Science archive is actually fantastic for results in social choice theory. And there's other journals you might consider getting alerts from: Mathematical Social Sciences, Theory and Decision. You can Google some of these more mathematical social science focused journals. Pursue multiple funding sources. External funding is hard if you decide to get external funding for an REU or something of that sort. And then finally, I'd just say, have fun with this. I did research with students in this area I've done it for, all of my career really. And it's been one of the most rewarding aspects of my career. And I think it has the potential to be both impactful and also a lot of fun. So I really appreciate your time today and allowing me to talk about some of this work and what I've learned from it. And here's just a couple acknowledgements for the funding sources for the research that I mentioned in this talk. So thank you very much.
Terrific. Thank you so much. It was an awesome talk. We do have a couple of minutes for questions in case anybody would like to ask anything. Scanning to see if hands are going up. Yes, Ismar.
I just have a quick question about, you mentioned that your student had come back to be a mentor or advisor at RU. Is that how your RU works, or is it all RU? Can faculty come from sort of anywhere and participate in a RU if you don't have maybe
Yeah, it depends on how you write the grant. That's a great question. So in that particular grant, we had always had only Grand Valley faculty in our REU. This is actually the only time in almost 20 years of the REU that we had an external faculty member, but we just wrote it in the grant. We talked to her beforehand, and there's certainly nothing, as far as I know, in the NSF or NSA guidelines that would prohibit multi-institution collaboration. It was really challenging to work with her organization to try to work out how to get her paid. That was non-trivial in ways that I didn't expect.
Awesome. Any other questions? We have time for maybe a very short question in case anyone has one. All right, well, let's thank Jonathan again for his excellent talk.
Thank you.
And we'll